Am I audible?
Yes, you are audible.
Okay. Okay, so good evening, everyone. I will start the class for today. Today is the 9th live session of the course Numerical Methods for Engineers. And this course is being handled on the NPTEL platform by Professor Niket Kaisare from IIT Madras. Today is the 9th live session. Today, the topic which we will be discussing is last class we had discussed on numerical differentiation, right? So today we will discuss about numerical integration. Why we need numerical integration and what are the possible techniques of numerical integration, and we'll look into some examples. Any doubts from the previous class, Nasim?
I don't have any doubt, but I wanted to ask
Yes.
when we are calculating the numerical values using the forward method or central difference.
Mm-hmm.
So the if the step size is very small, like of the order of 10 raised to power minus 4 minus 5. So the value of the function we have to take up to 7-8 decimal places.
No, that will be mentioned in the question.
Because this week assignment my question got wrong. I took a value up to 4 decimal places and I did subtraction and then answer came 0. So I reported 0, but answer was 0.0001805, something like that.
Then you have to, yes, it is nothing of that sort was mentioned in the question. Means how many decimal places you have to take.
Okay.
It will be mentioned in the question mostly. If it is not mentioned, if you are getting the same value, then just take one more decimal place. That will be better. Just to check.
Okay, got it.
Just a second. The screen is visible, right?
Yes, it is visible.
Okay. Okay, so I'll start today's class. So last week we had learned about numerical differentiation, or how to differentiate a function numerically, right? So today we'll be learning the next part of it, which is numerical integration, how to integrate a function analytically. We all know, but sometimes it may happen that there are different functions which are not possible to be integrated analytically, right? We have some complex functions of which formulas and all we don't know. So in such cases, we'll need the numerical integration techniques. So that's why actually that is the motivation behind doing integrating a function numerically. Or also you can say after this numerical integration in the next 2-3 weeks class, we'll be seeing ordinary differential equations, how to solve differential equations numerically. So there we'll be using all these concepts of numerical differentiation, integration, everything we will look into that, and we'll use these concepts there. So it is very essential that you understand these concepts of numerical differentiation and integration. properly. Otherwise, it will be a problem for you to understand the solving of numerical differential equations or ordinary differential equations. So we'll start today. So first we need to understand what do we mean by integration actually. Leave apart numerical integration, everything. First we will see what is integration. Then we will see why we need numerical integration. Then we'll go into it. Suppose you have a curve like this. Suppose some function is there, f of x. It is like this. And it is told that this is the lower limit of the function. Suppose this is the lower limit of the function a, and this is the upper limit of the function b. So if it is told that you have to find the integral of this function from a to b, f of x dx. So what do you mean by that? It is basically the area which is covered by the graph between these two limits, right? So this is basically the integral of a to b f of x dx. That is the area under the curve between the limits. Between the limits a and b. So this is basically the area. So now we need to understand that what we will do in numerical integration. This is the normal integration, right? The analytical integration, we have a functional form of f of x, and using the formulas which are available to us, the analytical formulas, we find out the integral of that function. But what we do in numerical techniques? So the way of integrating any function numerically is different for different methods. But first I'll tell you a very general method or a general perception of what we do. So what we do here is we basically divide this entire a to b interval in different subintervals. Okay. So suppose we have this one subinterval. Like this, we divide into multiple subintervals. Like this, we have multiple subintervals. So what is integral basically? The area, this total area under the curve is nothing but the sum of these individual areas, right? So suppose this area I am telling, the area of the first subinterval, I am saying it as A1. So the total like this, the next one is say A2. Like this, we have some n intervals. So this area, this integral a to b f of x dx will be the sum of all these areas, right? Is approximately equal to, it is not exactly equal. So what we can do is, if we can find some way to find these individual small areas, then we can sum up those areas and get our actual integral or the total area. Okay, so this dividing of this entire interval a to b into some small intervals, this process is known as discretization. In any numerical technique, any numerical integration or differentiation, the first step is you have to discretize. That is, you have a continuous function, right? This is a f of x is a continuous function here. So what we do is, you know the difference between continuous function and discrete function, right? So continuous function is which is continuous over a particular domain, and discrete function means it is only continuous that the value of the function is available at particular instance of time. So that is called a discrete function. So basically in numerical methods, what we do is we basically divide, or we basically subdivide a continuous function into multiple discrete functions, and then we discretely add those individual areas to get the total area or the total integral. So this is the basic essence of numerical integration. Is it clear to you?
Yes, understood.
Okay. So I'll just write down these points. First divide the entire interval multiple small subintervals. So this process is known as discretization. The smaller you divide, that is the width of this subinterval should be as small as possible. So if it is the step size, that is the discretization unit, that is the width of each of these intervals. Suppose this is like, I'm saying the width is h. This is h. All are equal intervals. Okay. So this h should be as small as possible. Then only you can your answer will be accurate, right? Okay. So this I'll write down here. When we go for numerical integration, either analytical integral. So integral is also called as antiderivative, right? So it is the opposite of differentiation. So it is also called antiderivative. Analytical integration is complex or not possible to evaluate. Then we go for numerical integration. Okay. So there are different techniques for numerical integration. First, we will look into the first technique, which is known as the trapezoidal rule. The first is, so this is basically what is trapezoidal rule. So first you need to understand what are the assumptions we are doing here. So this is applicable only for a first degree polynomial. A first degree polynomial, right? So what we do here, so suppose you have a function like this. So you have to find the integral of this function between a and b, okay, by trapezoidal rule. So what we do is, this function is not a linear function, right? So what we do, we first divide this function into multiple intervals, subintervals. So the process will be the same, just the way of approximating the function will be different. Okay, so now what we do is within these subintervals, if I just zoom in, you can see within these subintervals, we'll approximate this function by a linear function. Okay, so here the actual function between, say, the first limit is I am saying x naught, next limit is x1, right? So what we do between this x naught and x1, this function is exactly not linear. We approximate the function by linear. Similarly, between x1 and x2 also, we approximate the function by linear. Again, linear. Like this, discrete linear functions we assume. Okay. Like this we assume. Then what happens if you see each subinterval? I'll just draw it. So this is the subinterval, right? So this part is linear and you have a trapezium in the subinterval. The opposite sides are parallel and so it is a trapezium. So now we know what is the formula for area of a trapezium, right? So this individual, there are multiple trapeziums. So if we can find the area of each of these trapeziums and then add it up, we'll get the total area. So that is basically the trapezoidal rule. Is it clear or should I explain it again?
No, clear.
Clear, right? So what we
Yes,
do
clear.
here is, so first let us consider a function f of x defined in the interval a comma b, and then divide it into n equal divide into n equal subintervals. So what will be the width of each of the subintervals? The width of each subinterval, I'm taking it as h. So what will be h? There are n intervals and the distance is b minus a, right? So basically it will be b minus a upon n. That is the width of each interval. Clear?
Yes, clear.
Okay. So now, so if we try to find out what is the integral of this function, so what will be the area of the first trapezium? Where is it? Here, right? So this is x naught. The first interval is x naught and the second interval is x1. So now, what is the length of, we need the length of this line and the length of this line, right? So the left line, this length is functional value at x naught, f of x naught. And this length is basically f of x1, right? And what is the formula for the area of a trapezium? It is half into sum of the parallel sides, right? F of x naught multiplied by the perpendicular distance between them. So what is the perpendicular distance between them? It is basically h, right? Because this is the perpendicular distance between them, h. So what is h? H is here x1
Is minus.
minus
Yes,
x
yes.
naught, right? So this is the first trapezium rather. What will be the next one? Similarly, it will be f of x1 plus f of x2 multiplied by x2 minus x1, right? So this will go on. And what will be the last term? F of xn minus 1 plus f of xn. This is half into xn minus 1. So if we just simplify this, what we will get? So this, okay, 1 second. Summation I equal to 0 to n f of xi plus f of xi plus 1. This will be n minus 1. So since I'm starting from 0, it is n minus 1. If I start from 1, it will be n. Okay. By 2 into xi minus 1. So this is basically h, right? So it is, I'll just expand this. First will be f of x0 plus f of x1. Next term will be f of x1 plus f of x2. Next term will be f of x3 plus f of x4. Like this, it will continue, right? So it will be x n minus 1 plus f of xn. So now you can see from here, this x1 term is, so this f of x1 term is double. F of x2 is also double. Sorry, here. F of x2 plus f of x3. So f of x2 is also double. So like this, all terms will be 2 times except f of x0 and f of xn. Okay. So if we simplify and write, it will be basically h by 2 into f of x0 plus f of xn plus 2 into summation I equal to 1 to n minus 1. It is f of xi. Except the first and the last term, all will be double, right? So further we can simplify it and write. Okay, this is nothing, just x0 and xn are basically f of a and f of b, right? It is the lower limit and the upper limit. So this is basically I. So this is your formula for the trapezoidal rule. Is it clear?
Yes, yes, it is clear.
Okay, so this is the formula for the trapezoidal rule, right? So now we'll look into the next rule, which is known as Simpson's rule. So this is another rule of numerical integration, and this is generally used for the second and third degree polynomial, so third order polynomial. So in trapezoidal rule, what we basically did was we were approximating the function by piecewise linear functions, right? In each interval, we are assuming it as straight lines, that is linear functions, right? So now, when do you think this kind of rule will not work? Means when the error will be more. Suppose we just try to imagine this one. I forgot to tell. Suppose you have a function like this. So then, if you just if you take more subintervals, it is okay, but that is more computationally expensive, right? So if there are, suppose you take these 2 points and you approximate it by a straight line here. This one you approximate by a straight line. Again, you approximate by, but this is not accurate because the function is something else and you are approximating it as something else. So in those kind of situations, linear approximation will not work. So if linear approximation doesn't work, so basically your trapezoidal rule will give lot of error. Because here what happened is, here the function means we approximated it as linear, but the error was less because this you can see here. The blue function is the actual function and the green one is our approximated linear form of the function. So here the error was less because the function was almost close to linear. However, in the other example which I showed, this type of example of the curve here, so here the function is oscillating. So it's very difficult to approximate it by linear functions. If you take small intervals, obviously it is possible, but if the function values are more and the limit is too much widespread, and if you take very small subintervals, so that will be basically difficult, be computationally expensive. So in such cases, we don't use this trapezoidal rule. What we use is Simpson's rule. So what does Simpson's rule tell? So in Simpson's rule, there are two parts. One is the Simpson's 1/3 rule and the other is the Simpson's 3/8 rule. So in Simpson's 1/3 rule, what we do is we approximate the integrand, that is a function, approximate the function by second degree polynomial. And in the other rule, that is Simpson's 3/8 rule. We approximate the polynomial by approximate the function by third degree polynomial. Okay, so first we'll talk about the Simpson's 1/3 rule. So what we do here is we have 3 points of discretization here. So the first point of discretization is the lower limit, that is x1 equal to a. Second point of discretization is a plus b by 2. The third point of discretization is b. So this is the functional value here is basically f of x1. This is f of x2. This is f of x. Okay. So how we approximate the integrand? So basically we use in interpolation, I had talked about Lagrange's polynomial, right? So we use Lagrange's interpolating polynomial to predict the second degree polynomial, which closely mimics the function or the integrand. Oh. So basically what we do here is we use the Lagrange's interpolating polynomial. Using that formula, we basically try to predict second degree polynomial, which closely fits the actual integrand or the actual function in those subintervals basically. So what we were doing is, again, I'll repeat this concept because this is very important. In trapezoidal rule, we divided the entire function into subintervals, and within those subintervals, we approximated the integrand as linear functions. What we do in Simpson's 1/3 rule is we divide that function into multiple subintervals. However, in each subinterval, we here use Lagrange's interpolating polynomial to predict a second degree polynomial. That is a second order polynomial of f of x square. So that we do, which closely mimics the integrand. Is it clear? Any questions?
Yes.
Okay. Okay. So here basically, I'm not going into the derivation here because that is very complex. So what we will get a to b here. H is basically the gap between the intervals, right? So h by 3 f of x1 plus f of x3. So I'll show this by the graph here. So suppose you have a function like this. Suppose you have the 3 points here, right? So this is A, this is B, this is the midpoint, A plus B. So this type of function in each of these subintervals, we basically approximate it with a second order polynomial, right? This is a second order polynomial, another second order polynomial. Fine. And this is H. This is also H. Now we can easily understand this is A means this is X1, this is my X2, this is my X3. This is the Simpson's 1/3 rule. So now you might ask a question that what if I divide this function into multiple subintervals, right? So that is basically called as composite Simpson's rule. We'll also look into that, what happens there in composite Simpson's rule. So before that, is it clear how to evaluate and why are we doing like this? Is the concept clear?
Yes, yes, it is clear.
Okay. We'll see the composite rule also. So in composite Simpson's rule, so suppose you have a function like this. Suppose we have a function like this. Okay, so now we may not want to only to discretize into two subintervals like I showed here, a, b and a plus b by 2. So that is not accurate, right? So if you, as I told, if the h is much smaller, if it is the small you can make, the more accurate your answer will be. Because then you get a smaller subinterval and within each subinterval, that function, that error between the approximated function and the actual function will be less always. So like this, what we do here is, suppose this is my A and this is my B. Okay. So here we take a subinterval, like we do like this. Within this subinterval, suppose this is my say x naught and this is my just xn. So you have a subinterval here. Suppose this is my subinterval. This is my x1. This is my x naught plus x1 by 2. So this one set of x naught, x1 by 2 and x1 is the same as this one. This a, b and a plus b by 2. So this is actually one unit. Again for the next subinterval, we have another unit. Then we have here we have say x2. Then we have x1. One second. Suppose we have this subinterval. So this is basically x1 plus x2 by 2 and this is x2. Like this we continue. Multiple sub units basically. So one unit comprises of x0, x1 and their midpoint. Then the next unit again will be x1, x2 and their midpoint. So in each of these subintervals we'll apply this Simpson's rule and then we'll sum up everything and get the total formula. Is it clear?
Yeah, is there any means way means how will we determine how many subunits we will need?
That will be given in the question. H will be basically given in the question. The step size.
Okay, okay,
The discretization
okay,
unit. That
okay,
will be given in the question.
okay.
So now, if I just add up all and if I simplify this, what we will get? A to B fx dx. So this, if I just sum up, equals to, it is basically equal to h by 3 f of x naught plus f of xn. First and last term will be ones. Then we'll have 4 into summation of, one second, I'll just replace this. This I'll represent by x1. X1 will be x2. This will be xn plus 1. Just I've changed the notations. F of x1 is first and last term. Then we'll have I equal to 2, 4, 6, dot, dot, dot. That is the even terms will come here. 4 times will be the even terms and the odd terms 1, 3, 5 up to n minus 1 will be 2 times. So if you just apply this above formula into this each of these subunits and then sum up this, we will basically get this formula. So this is basically the Simpson's 1/3 rule for calculation of integral, numerical integral using Simpson's 1/3 rule. So this is the formula. Is this formula clear? Because you need to remember this formula to calculate the integrals, whatever will come in the assignment or in your exams. I'll do the problems obviously, but is this notation or everything clear to you? And remember that your numbering of the discretization starts from 1, not from 0. If you start from 0, then this formula will change, because then the even terms will be 2 times and the odd terms will be 4 times. Just follow this notation. That first limit is x1, then x2, like that it will go on xn till xn plus 1. So if you follow this notation, then this formula is correct. Clear, right?
Yes, yes, it is clear. And this composite Simpson's rule, it's for oscillating functions.
It can be for any kind of functions.
Okay, okay.
Clear, right? We'll go to the next rule then.
Yes, yes, it's clear.
Okay. So next you have for Simpson's 3/8 rule, right? So in Simpson's 3/8 rule, what we basically do, in 1/3 rule, we approximated the function as a second degree polynomial, right? So here we approximate the function using a third degree polynomial. That is a cubic polynomial basically, or a cubic polynomial. So previously in the Simpson's 1/3 rule, we had 3 points, right? A, B, A plus B by 2. Here we'll have 4 points. 4 points of discretization in each unit. So now I'm not talking of the composite rule. I'll come to it later. So the first point of discretization is x1, which is equal to A. Functional value is f of x1. Then I have x2, which is 2a plus b by 3. Then I have x3, which is a plus 2b by 3. And x4, which is b of x2. So just remember here, if you just subtract x2 minus x1, what is h here? Is basically x2 minus x1. So what you will get, 2a plus b by 3 minus a. So it is basically b minus a by 3. For all the remaining things, that is trapezoidal rule and Simpson's 1/3 rule, h was b minus a by 2, right? So here we have h equal to b minus a by 3. Just remember this thing. Okay. And similar kind of thing as we did in 3/8 1/3 rule. Right. So suppose you have some function your second point, your third point. Right. So now you approximate it by a cubic polynomial, right? cubic polynomial will look like this. In this individual subintervals, you have to look for the cubic polynomial. So this might look like a, the drawing is not correct. This will look like a third degree this is the this is your x naught, this is x1. Sorry, this is a this is a lower limit and the upper limit, and the individual points x1 and x2 I have told. X1 is 2a plus b by 3 and x2 is a plus 2b by 3. Right. So now if we go for the composite rule as I described previously, that is if you want more subintervals, then what we will do, we'll just, this is 1 unit, whatever I have shown here, this is 1 unit, right? So if we take multiple units within one interval, so that will give rise to composite Simpson's 1383. So that will be basically 3h by 8. Okay, first I did not write for the normal one. No? So for Simpson's normal 3/8 rule, this is not for composite. This is when there is only one unit. A to B, f of x dx will be basically 3h by 8 x2, 3f of x3 plus f of x, or f of xn rather. So x1, x2, x3, x4, right? So x2 and x3 will have three times, and this will be one time only. So now if I go for the composite rule, a to b f of x dx equals to 3h by 8 f of 3h by 8 into f of x1 plus 3 times 2, 5, 8, 11, like this terms will be f of xi plus 1. This is within bracket, okay? This is 3 times. Then we have 2 into summation, the remaining ones. 1, 4, 7, like this up to n. We will have f of xi only, plus the last term, which is xn. So this formula is a bit complicated. You just remember the 2, 5, 8, x2, x5, x2, x3, x5, x6, x8, x9. Like this, all these will be 3 times. And so this is the Simpson's 3/8 composite rule. Okay. So now we will see with the one function we'll take one integrand, and then we'll apply all these rules, whatever we have learned, and then we'll see which one is more accurate and which one is less accurate. We'll see. Okay. Just 5 minutes break I'll take, then I'll come back.
Okay, okay, sure.
Okay, so I'll start the remaining part. You are here, right, Naseem?
Yes, I am here.
Okay. So now we will look into a problem and we'll see which rule is more accurate and what are the errors involved. Everything we'll look into it with an example. So suppose you have an integral to calculate 0 to 1.2 and this is your function. Okay. So this is your function. So now first we'll try to evaluate it analytically. So analytically, if we try to evaluate, it will be 0.2 e to the 1.5x dx. So integral of e to the power ax is check my calculator just a second. So if we just substitute this, how much we'll get 0.2 by 1.5 multiplied by 1. So analytically, the answer is 0.67328. So this is the analytical or the true value. This is the true value of the integral. So now we will take each value and each rule we will take. We will take the first the normal rule and the composite version of that rule, and then we will find out which one is more accurate. And with respect to this we'll consider as the true value. So the first one is trapezoidal rule, right? So first is we'll take the normal trapezoidal. So what does normal trapezoidal rule say? It is I is h by 2 f of a plus f of b, right? So h we will first, we have to decide what is h. So in trapezoidal rule, what is h here? H is basically b minus a, right? And we are dividing the interval into only one subinterval, right? So h is b minus a by 1 here. So it is basically 1.2. So now if we substitute this, just a second. Okay. So h is 1.2 by 2. Just a second. Um, okay. H is 1.2 by 2. F of a. What is a? F of 0 plus f of 1. So it is 0.6 into 1 plus 1 second, 1 second. Sorry. F of 0 is 0.2, right? Plus 0.2 e to the power 1.5 into 1. So it is 0.2. If we just take common, it will be 0.12 1 plus e to the power. How much it will be? 15.8. 1.5 into 1 plus e to the power 1.8 into 0.1. So it is coming around 0.84595. So if we see this and if we see the actual value, it is huge difference is there, right?
Yes, it is very much deviating.
It is very much deviating. So because if we try to plot this function e power ax, so just try to understand what we are basically doing here. So e power ax will something look like this, right? So basically, so what we are doing is this is my a and this is my b, right? This is my 0 and this is suppose 1 point. Okay. So what we are doing here is we are just basically approximating it by a straight line, and we are finding this area, right? Whereas what is the actual area? The actual area is only this area, right? It is only the lower area, not the upper one. But since we are approximating it by a straight line, we are overestimating the area. So this is actual. So this value is actually what we got analytically, 0.67528, whereas the total one, that is this one, 0.84595. So you can understand that using the normal trapezoidal rule, if we do, we are getting a lot of error because the function is not linear and you are forcing it to be linear. So obviously there will be a lot of error, right? Is it clear?
Yes, clear.
Okay. So now we will see composite Simpson's rule. Okay. So first one we got. Now we will do using composite trapezoidal rule. So composite trapezoidal rule. So previously h was b minus a by 1, right? So here we are just increasing one more interval. So we are doing h equal to b minus a by 2. It is basically 0.6. Okay. So what will be I now? I is h by 2 plus into f of 0 plus 2 into f of 0.6 plus f of 1. So it is basically 0.3 into what is f of 0, 0.2, 2 into what is f of 0.6, 0.2 e to the power 1.5 into 0. So it is 2 into 0.4919, 1.2, 1.209. So if you find out how much is this, 0.3 into 0.2 plus 2 into 0.4919 plus 1.2099. So this is coming around 0.7181. So you can see the actual value was how much? 0.67328. And this is from single trapezoidal rule, we got 0.84595. Now, if you use composite trapezoidal rule, that is trapezoidal rule with a lower value of h, it is 0.71811. So this is more accurate, right? So as you decrease this h, that is, as you reduce the step size or as you increase the number of sub intervals, your actually your answer is becoming more accurate. Is it clear?
Yes, it is clear.
Clear, right? Just one more we will see here. If we take h is 0.3, what will happen? So now you have 0, which is x naught. Now you have 0.3, which is x1. Then you have 0.6, which is x2. Then you have 0.9, which is x3. And then you have x 1.2, which is xn. Okay. So now what will be my I? Can you tell me, Nasim, what will be my the formula here?
H upon 2 f of
Huh?
0
Yes.
h upon 2 bracket
Huh?
f of 0
F of 0.
plus 2 times like even numbers,
Not
not
even. Oh, this is
even
trapezoidal rule we are doing, right? Here there is no concept of even and odd. That is in Simpson's rule.
okay.
Here only the first term and the last term will be one time and all others will be two
Okay.
times. Okay.
2 times, okay.
So it is 2f of 0.3, 2f of 0.6, 2f of 0.9 plus f of 1 point. So if you find this one, how much it will come? We'll see. F of 0 is 0.2, f of 0.3 is. So what do you think? This one will be more accurate or less accurate?
It will be more accurate.
Yes, because we have
the
reduced
step size
h.
is, yes, yes.
0.6 we have seen. Say for 1.2. 0.6. Now it is 0.68459. So this is more accurate, right? So you can easily see the error percentage are reducing. So is this concept clear that if we are reducing h in trapezoidal rule or any kind of rule, your error will reduce. And why that error will reduce is that graphically is that approach clear to you, means is that figure is clear in your mind, right?
Yes, I understood.
Okay. So next we will see Simpson's rule. Just 1 minute, I'll come back. Okay, so now we will see the Simpson's 1/3 and the Simpson's 3/8 rule. Okay, how to what is the error or what is the thing. So in Simpson's 1/3 rule, first we'll see the normal Simpson's 1/3 rule. Then we will reduce h and then we'll see what is the thing. Okay. So in 1/3 rule, what all points we have? X naught, that is A. Then we have X naught, which X1, which is how much? A plus B by 2. Then we have X2, which is B. Okay. So here X naught is 0. This is 0.6. This is 1.2. Right. So what is I here? It is H by 3 f of X naught plus 3 times, most probably 4 times 1 plus f of x2. So what is h here? H is 0.6, right? F of 0, 4 into f of 0.6 plus f of 1.2. So if you simplify this, you will get 0.2, 4 into 0.4919 plus this one was how much? 1.091. So if we sum up this, so this is coming around 0.675. So now just notice this one. Using Simpson's 1/3 rule, we are not using composite rule still. But still the error, if you see, is much less compared to the trapezoidal rule. So in normal trapezoidal rule, we got 0.84595, where the true value was 0.673. Whereas using the normal Simpson's rule, we are getting 0.6755. So what does this tell you? It basically tells us that so this function is like this, right? Is somewhat like this. It's not exactly like this. So now if you try to approximate this function in a linear way, it will not be correct, as I showed in the previous video. But since this is almost looking like a parabola, that's why in Simpson's 1/3 rule, we approximate the integrand by a second order polynomial. So that's why since this function is almost like a approximating that function using a parabola or a second order polynomial would be most accurate. And that's why the error in Simpson's 1/3 rule for this particular type of function is less. Is the concept clear? Is it clear to you what I'm trying to tell?
Yes, I understood.
Okay. So this is the thing. So whether the trapezoidal rule will be accurate or whether the Simpson's rule will be accurate, that basically depends on the type of function you are integrating. All right. Now we will use the Simpson's 1/3 rule composite. So in composite rule, in 1/3 rule, what we have that even and odd thing, right? So here we have x naught equal to 0, x1 equal to say 0.3, x2, 1 second. Here we have to change the notations. In Simpson's rule, always it should start with x1, 0.6 and x4 equal to 1 point. So I will be h by 3 f of x1 plus f of x4. Then we'll have the even terms. Even term will be 4 times and
Four times.
odd term will be
Two
2
times.
times. So if you would have more even terms here, except the first and the last, we have only one even term and one odd term, right? So that's why it is 4 into f of x2. If some other term was there, we will all add up all those things. Okay, so what is h here? H is 0.3. 0.3 by 3. F of 0. F of 1.2. 4f of 0.3. 2f of 0.6. So it is basically 0.2. 1.2099. How much is 0.3? We calculated, right? 0.3 is 13136. One second, I did one mistake. So this is the actual discretization, right? 0, 0.3, 0.6, 0.9, 1.2. So it will be basically, some changes will be there. F of x5. And we have two odd even terms, right? So it will be 4f of x2 plus 4f of x4 plus 2f of x3. So if we just write it again. So it is basically 0.1 into f of 0 plus f of 1.2, 4 into f of 0.3 plus f of 0.9 to f of, so it will be basically 0.1 into 0.2 plus 1.2099, 4 into 0.3136 plus, I think, how much was it? 7715. 7715. 2 into 0.4919. So if we do this 1.4 into 0.3136 plus 1.75 plus 2. Just 0.67341. What was this one? It was 0.675 and actual was 0.67328. So here in composite rule is always more accurate than your normal rule. So this is again proved here. So up to 3 decimal places it is matching with the actual rule, right? Clear? Is it clear?
Yes, clear. Yes.
Okay. So now we will look into two more concepts today. The 3/8 rule I'm not doing. You can try it out on your own. It will be the same thing. Okay. So now we will look into another concept which is called as Richardson's extrapolation. So this is another technique of numerical integration. So we will use here normally trapezoidal rule for better, how we can use trapezoidal rule only for better approximation. So what we will do, so what is your true value of any integral? So it is basically the estimated value plus the error term, right? So this is the estimated value using, say, here we are looking into trapezoidal rule. So it is basically estimated value using trapezoidal rule, and this is the error, right? So suppose we are using the trapezoidal rule, and two times we use the trapezoidal rule, one with a step size of h1, another with the step size of h2. Okay. So when we are using a step size of h1, we are writing it as I of h1. That is okay. I of H1, and when you are using H2, it is I of H2. Okay. So what we can write here is I true if we are using step H1, I of H1 plus E of H1. So now when we are using step size H2, your true value remains same, right? So true value doesn't depend on your numerical technique or your step size anything. So we can write I of H2 plus E of H2. Correct? Is this clear? What I'm trying to tell here?
Could you repeat it once again?
Yeah. So actually I'm telling that the true value of any integral, that is what we are getting using an analytical technique. So that is basically not your estimated value. It is the exact value, right? So what is the difference between the true value and the estimated value? It is the error. So basically I'm trying to tell that the true value is equal to the estimated value plus the error, right? So now this estimated value will depend on your step size h. So I'm telling that using the trapezoidal rule, I'm trying to approximate the integral first using a step size h1, then using a step size h2. However, with the change in h, your estimated value will change. That is, your trapezoidal rule will give you a different answer. However, the true value, that is the analytical value, that will not change. That is independent of your step size or the numerical technique you are using, right? So based on that, I have written these two equations. What I have written, the first equation is I true is equal to I of H1 plus error of H1. Similarly, when I use H2 also, your I true will remain the same. Is this clear to you?
Yes, yes, I understood.
Is it clear, Nasim?
Yes, yes, it is clear.
Okay. So now, based on equations 1 and 2, we can equate this, right? I of H1 plus E of H1 equal to I of H2 plus E of H2. And in trapezoidal rule, I have not told you this one, your error is always proportional to the square of step size. This you must remember. This is for trapezoidal rule. Okay, so if your h increases 2 times, your error will increase 4 times. Similarly, if you reduce your h by 2 times, your error will reduce by 4 times. So your error is proportional to h square. So what we can write, E of h1 by E of h2 equal to h1 square by h2 square. So now if we substitute this one here, I of h1 in place of E of h1, I am substituting E of h2 into h1 square by h2 square equal to I of h2. So then we will get E of h2 into h1 square by h2 square minus 1 equal to I of h2 minus I of h1. So now from this, if I try to find out what is error using step size h2, so it is basically I of h1 minus I of h2 by h1 square by h2 square. Sorry, I of h2. So this is E of h2. Okay. So now what will be I true now? I of h2 plus E of h2. Right. So I of h2 is I of h2 plus I of h2 minus I of h1 by h1 square by h2 square minus. This is I2. So now if I just substitute h2 is equal to h1 by 2 equal to h by 2. That is the second step size is half of the first step size. So what will be I true? If you substitute this, you will basically get 4 into I of h by 2 minus I of h by 3. So using this, if we find the order of the error will be of order O of h power 4. So you can see here that this is a better approximation. Using two trapezoidal rules and some manipulation in the values, we can come up with another formula for any integral. We'll find using trapezoidal rule, we'll find the integral estimated with step size h, then with h by 2, and we'll use this formula to get the actual value of the function. So here the error will be less and it will be a better approximation. Is it clear?
Yes, it is.
Clear, right?
Yes, yes.
Okay. So we'll see this.
One
Yes,
thing,
yes.
could you means previous slide?
Previous page. Yes.
Can you play this square in the trapezoid by graphically?
Yes. Once again, can you come up? Your voice is breaking.
The error is proportional to h square. Can you explain it means graphically?
So graphically, there is nothing to explain actually here. So if you just find out, you can, okay, I'll just try. So suppose this is your function, okay? So suppose the first I'm using this h. The whole thing I'm trying to represent by a straight line, okay? So you can understand what is your error here. Your error is this part, right? Is it not? Your error is this yellow part because when you are approximating by a straight line, whatever is below this black straight line will be the estimated one, whereas the actual one is below the this curve. So your extra part will be this yellow one. This is your error. So here h is the entire thing. Okay. So now if I just replace it, now my points are this one, say this 3 points. So your h is halved now. So now your error should reduce, right? So this is one straight line. This is my another straight line. Okay. So now if you find out the errors, can you tell me what are the errors now?
Errors are means yeah, this area and that area, small areas, not the whole yellow area.
Yeah. So this is your new error now. Some of these red areas, right? So you can see here clearly that if I reduce h, then your error is reducing. But this h square thing, I cannot show it graphically. You can do it and find out.
Okay, means if it is half, then error is 1/4.
Yes, correct.
Understood.
Fine, right?
Yes, yes, fine.
So this Richardson extrapolation, we will see that whether it is more accurate or less accurate. We'll try to see. So I'm taking the same integral. It was 0 from 1.2 e to the power 1.5x dx. So here first we will take h equal to 1.2, h2 is 1.2 and h1 is 0.6. So I of h2, if you find out using trapezoidal rule, you will get this one, right? First we evaluated this. And I of h1, that is using 0.6, you will get 0.7181. So now, using your Richardson extrapolation, you see what will be your I now? I true is 4I of 0.6, I 1.2. So if you substitute these values, you will see you are getting 0.6755, which is more accurate than your 0.7181 or 0.8459. So you can easily understand that using this Richardson extrapolation, we can easily get a more accurate and a better approximation to the integral. Clear?
Yes, yes, clear.
So the last topic for today, it is another technique of numerical integration. So it is known as Gaussian quadrature. So we'll try to understand what is Gaussian quadrature. So we are just trying to represent the integral in a particular form. I'll tell what are these variables. So any that function here is f of x, okay, the integral. So basically we are trying to find out some coefficients c0 and c1 and two values x0 and x1 such that this true integral can be represented in this form. That is c0 f of x0 plus c1 f of x1. Whether we can represent it in this form. So how many unknowns are there? Here there are four unknowns, right? c0, c1, x0 and x1. So in order to find the true integral, we need all these four values. So how can we get that? So we'll do some manipulations and mathematical algebra normal that has nothing to do with your numerical techniques. Okay, just take first you take fx equal to 1. So then what will be I? And the limit I am always considering -1 to 1. Okay, so it will be 2, right? So now if I try to represent this as in the form of Gaussian quadrature, it will be basically c0 into f of x0 c1 f of x1 equal to, what is x0 and x1 here? X0 is -1 and x1 is +1, right? So f of x is 1. So c0 into f of -1 c1 f of 1 equals to. So f of x is 1. So it is c0 plus c1 equals to. This is one equation. Next, if we take fx equal to x, what will be my integral? It will be 0, right? So if we again substitute like this, c0 into f of -1, c1 f of 1 equal to 0. So it is c1 minus c0 equal to 0. So from these two equations, we can easily find out c1 and c0. c0 will be equal to c1 equal to half. So next, there are two more things remaining, that is x0 and x1. So third case, we will take fx equal to x square. So if we write it like this, x square integral will be 2 by 3. So c0 and c1 we know half, right? So this will be 1 second. Mistake. 1 by 3. So x0 square plus x1 square will be equal to 2 by 3. So this is equation 3. One more equation we need. So we will take fx as x cube. So it will be c0 x0 cube, c1 x1 cube equal to -1 to 1 x cube dx. So x0 cube plus x1 cube equal to 0. So we'll get x0 equal to -x1. This is equation. So if we solve equations 3 and 4, If you solve this, we will get x naught equal to 1 by root 3 and x1 equal to minus 1 by 3, or vice versa also you can take. So C naught we have got C naught equal to C1 equal to half, and x naught and x1 are 1 by root 3 and minus 1 by root 3. So using this, now we can find any integrals. And one more thing we have to do here, all our integration, whatever C naught, x1, x naught, C1 we have got, all are for the integral limits minus 1 to 1. So you have to change your integral limits in your actual answer if it is not minus 1 to 1. So how we will do that? Up till this, is it clear?
Yes, clear.
Okay. So now we will look into the change of variables. So how do we change the variable, right? So suppose you have your integral from a to b, your fx dx. So this you have to change to minus 1 to 1, some function of suppose y I am telling dy. So you have to find out your y here. So how will you replace x so that your limit changes from a to b? A to b changes to minus 1 to 1. So 1 second. So we'll do it with one example, right? Suppose you have the same integral. So before applying this Gaussian quadrature on this, we have to change the limit, right? So if we do 1 second. How to do the change of limit? 1 second. We want it from minus 1 to 1, right? Okay. So suppose I assume it is x as a naught plus a1y. Okay. So at x equal to your lower limit, how much is x? Your 1 second. A equal to a naught plus a1. Y we want it as first as minus 1, right? So your a naught minus a1 is a. This is your first equation. And at x equal to b, that is the upper limit. B will be equal to a naught a1 into. Therefore, a naught plus a1 will be b. So if you solve these two equations, your a naught will be a plus b by 2, and a1 will be b minus a by 2. Right? If you solve these two equations, a naught equal to a plus b, and a1 is b minus a by 2. So now we will substitute in the actual thing. X is a plus b by 2 plus b minus a by 2 into y. So this is your changed variable. You have to replace x by this. Similarly, if you change x, you have to change dx also. Right? So what is dx? This is constant, b minus a by 2 into dy. So these are your changed variables. So how is it clear, or should I explain it once again?
No, it is clear.
So now how to use this, right? So your question was 0 to 1.2. So here we will, your a is 0, b is 1.2. So x will be 0 plus 1.2 by 2 plus 1.2 minus 0 by 2y. So it is 0.6 plus 0.6y. So basically in place of x, we have to replace this, and dx will be 0.6 dy. So if we replace this, limit will change from -1 to 1. 0.2 e to the power 1.5 into 0.6 into y plus 1 into 0.6 dy. So 0.2 and 0.6 will be 0.12 1 e to the power 0.9 into y plus 1. So now this one we have to evaluate using Gaussian quadrature. So what does Gaussian quadrature tell? It is C naught f of x naught f of x1. C naught and C1 are half, right? So it is half of f of 1 by root 3, f of minus 1 by root 3. So if you substitute this, C naught and C1 were half, right? So it will come as f of 1.5.
It's a correction. It will be C1F.
Yes.
In the second means half multiplied by f of minus 1 by root 3.
Yes, I've given the bracket I've given, no?
In the second C0 and C1 both are half now.
Yes, I've given bracket, that's why.
Okay. Understood.
1.5 by 3. Yes. It is around 0.6718. So you can see using Gaussian quadrature also, it is more accurate than your trapezoidal or your Simpson's rule. Okay, so is the thing clear? All the techniques are clear. You can go, I'll upload these notes in this Google Drive link, which is being shared with you. You can go and look into this.
Can you give a quick recap of this Gaussian quadrature? Just a quick recap.
Yeah, sure. So Gaussian quadrature, basically, the true integral, we are trying to represent it in the form of sum of the functional values of two functions, right? C naught into f of x naught plus C1 into f of x1. So using different sample functions, fx equal to 1, x square, x cube, we obtain the values of C naught, C1 as half, and x naught and x1 as 1 by root 3. X naught as 1 by root 3 and x1 as minus 1 by root 3. Okay, so now one of the main problems here is whatever we evaluated this C naught, C1, x naught, x1, all are for integral limits of -1 to 1. So if your question comes in which the limit is not -1 to 1, so what do you need to do? You have to change the limit to -1 to 1. So if you want to change to -1 to 1, you have to accordingly change your integral variable also, right? So how I did that? So you can see here, your limit was from 0 to 1.2. So I took x as a naught plus a1 into some new variable y. So at x equal to a, that is the lower limit. If I substitute in this equation, we will get one equation a naught minus a1 as a. And at the upper limit x equal to b, if we substitute, we'll get a naught plus a1 equal to b. If we solve these two equations, we will get a naught and a1. Then we go back and substitute in place of a naught and a1 in the equation for x. So from that we get x equal to a plus b by 2 plus b minus a by 2 multiplied by y. So if x changes, obviously since its differential is also involved, which is dx, that will also has to be expressed in terms of y, that is dy. So if you just differentiate x, the first term a plus b by 2 is constant. So obviously differential will be 0. And the second term b minus a by 2 into dy. So this I have just employed here. So a was 0 and b was 1.2. Similarly, I found out x in terms of y, which was 0.6 multiplied by y plus 1, and dx was 0.6 dy. Then I just substituted this in this equation, and I got the integrand as 0.12 e power 0.9 into y plus 1. So here one more term will come multiplied by 0.12. So this will f of 1 by root 3 and plus f of minus 1 by root 3 both multiplied by half multiplied by that 0.1. Is it clear now?
Yes, it is clear.
Okay. Just go through it once again after I stop the class. It will be clear. If you have any problem, you can ask in the next class. Okay.
Okay. Could you upload all the means previous lecture,
Ha.
like from
Yes,
week
yes, I
5?
will
It is
upload.
not uploaded.
Ah.
Okay.
Okay, fine. Then we'll meet next Saturday, 7 o'clock. Okay, evening.
Okay. Bye. Goodbye.
Okay, fine. Bye.